So now I want to talk about variations of hopfield models, different versions of that. Every day we have a different version of that in computational neuroscience, because we want to add, for example, the continuous version of that. We want to add the spiking neuron version of that. And so we have different models of hopfield networks. So we fall into local minima. This is a problem. This is a challenge in hopfield networks. So let's see how can we get around this problem by inventing something such as noise, for example, by inventing something like continuous domain instead of just discrete states. So once the weights of the edges have been defined, the network shows spontaneous computational properties. Harnessing this spontaneous dynamics for useful computations requires some way of avoiding falling into local minima of the energy function in such a way that the global minimum is reached. In the case of 8 queens problem, the number of local minima is much higher than the number of global minima. And very often, the hopfield network does not stabilize at a correct solution. So it is stabilized at something, for example, this is the correct solution, but it is stabilized at this point, at this point, different memories. So there are 2 strategies, as I said, to overcome falling into local minima. One possible strategy to improve the global convergence properties of a network consists in increasing the number of paths in search space in such a way that not only binary but also real-valued states becomes possible. So that's the continuous updates of the networks. The other one is introducing noise. As usual, the network will reach states of lower energy, but will also occasionally jump to states higher up in the energy ladder. In a statistical sense, we expect that this extended dynamics can help the network to skip out of local minima of the energy function. The best known models of such stochastic dynamics are Boltzmann machines. And of course, restricted Boltzmann machine is invented by Geoffrey Hinton. Everybody knows that. It's a very important thing. So we have local minima, and if we have a noise here, it jumps into global minima, so it's very good. So the hopfield model with binary or bipolar states can be generalized by accepting, just as in backpropagation networks, all real values in intervals possible unit states. Consequently, the discrete hopfield model becomes the continuous model. The activation function selected in the sigmoid, and the dynamics of the network remains asynchronous. The difference between the new and the discrete models given by activations assumed by unit I, once it has been asynchronously selected for updating. So the new state is like this. UI is the net excitation of the unit. Additionally, we assume that the unit's excitation changes slowly in time. Changes in the state of other units will not be registered instantaneously, but with a certain delay. The net excitation of unit I changes in time according to this differential equation. So the nonlinearity comes here, because this function is nonlinear with respect to UI. So again, we have energy function, but here we integrate over all xi's, because x could change. It's not just 0 or 1. You should integrate over all possibilities. But the important thing is that if you just make derivative with respect to time, then you will see that that decreases as well. So again, we have something like Lyapunov function, like an energy function, that is reduced, and it converges to some extremum, some minimum. The continuous model, the time needed for convergence can increase exponentially since the derivation gets small and smaller. We must therefore require convergence to a neighborhood of a local minimum, and this can happen in finite time. So this is a kind of stochastic neural network. We want to define a Boltzmann machine like this. A Boltzmann machine is a hopfield network composed of n units with states x1 through xn. Of course, they use different meaning of states, but it depends on this. Depending on the situation, you should distinguish between these things. Otherwise, it becomes complicated. The state of unit I is updated asynchronously according to this rule. So we say with this probability, it is 1, and with 1 minus this probability, it is 0. And T is a temperature. Even in ChatGPT, we have the concept of temperature. So it's very important. In physics, we have in simulated annealing, if you're familiar in artificial intelligence. And of course, it has its roots in metallurgical processes. But the concept of temperature is very important because we have a different set of dynamics with different. So it's a measure of susceptibility, in my opinion. The difference between a Boltzmann machine and a hopfield network is the stochastic activation of the units. So if temperature is very small, then that probability is very close to 1 if it is positive. And if the net excitation is negative, then it becomes gets closer to 0. In this case, the dynamics of Boltzmann machine approximates the dynamics of discrete hopfield network. A Boltzmann machine settles on a local minima of the energy function. If temperature is greater than 0, however, the probability of a transition or a sequence of transitions from network space x1 through x sub n to another state is never 0. The state space of the Boltzmann machine contains 2 to the n vertices of the n-dimensional hypercube. When a network state is selected, we are choosing a vertex of the hypercube.